Hello everyone and welcome to this video. In this video today I'm going to discuss to you about Diophantine equations and how can we tackle them if they appear in the exam. So since pre-RMO is above the edge and it's very soon that we have to give the pre-RMO and the likes of ISI and CMI if you're also preparing for that. So this video is targeted for any age group who is trying to prepare for mathematical Olympiads or maybe trying to give entrance examinations into premier institutes like ISI and CMI. So today in this video we are going to discuss about some basic techniques and some tricks to tackle Diophantine equations. See, Diophantine equations basically is a part of number theory, and to understand this is very simple, but to do them is equally hard. So Diophantine equations are the equations which are consisted of integers. Okay, so let's say we have an integer x and y. So an Diophantine equation in an x and y could look something like this: x cubed plus 2 equals to y square. So this can be called as a Diophantine equation as the entries involved are integers x and y, and this is unlike what we have learned in our classes. This is not that when we have two variables we need two sets of equations. So this is the magic of number theory, that it doesn't matter how many equations, how many variables are involved in that equation. So you might be given only one equation, but you might have to solve it for all pairs of xy that satisfy this, given that they're integers. So it is pretty natural to understand that whenever these entries are integers, things change a lot. That means any kind of equation becomes very much tractable. It can really be tackled using the tools of modern number theory and the tools of Diophantine equations, which we are going to discuss in this entire lesson. Okay, so to begin off, let's first check a few equations and how to solve them. So firstly, let's say we have an equation of the type equations of the form. Let's say you have an equation of the form x square minus y square equals to 3, given that x and y are integers. And if someone asks you, is there a possible solution to this equation? Well, there are a lot of answers to this. So the thing is, firstly we can actually use a method called factorization, which all of us have learned how to factorize equations, how to factorize polynomials. So here we are simply going to try and do factorization, because integers have a property that they can be factorized into prime factors, and whenever the integer on the right hand side or on the left hand side is itself a prime, that gives us a plus advantage. So here we can say that x plus y into x minus y using the formula for a square minus b square. The answer is 3. So the product of two numbers which are integers themselves is 3. Now 3 is a prime, and we can always say that 3 can be written in only one way, that is 3 into 1, if ordering is not taken, because you can also write this as 1 into 3, and there are no more representations possible. So that means if we assume without loss of generality, which we call as W log, that x is greater than y, then we can simply say that x plus y and x minus y, between these two expressions x plus y is the greater one, and thus x plus y must be the one which is equals to 3. That gives us x plus y equals to 3, and the other equation x minus y equals to 1. Solving these two equations gives us the values. By adding them and dividing by 2, you get x equals to 2, and putting in this you get y equals to 1, and this actually completes our proof that this is the only solution to this equation if x and y are positive. Obviously there are more solutions, because if we are taking negative integers into account, we can always write minus 2 and 3, minus 2 and 1, then 2 and minus 1, and so on, right? So there can be various solutions, but all of them will have the absolute value of 2 and 1. So you see, factorization is a technique which can be very handy if the number residing on the other side is actually factorizable. And if you can factorize it into a product of prime factors, then always you can equate the factors in terms. Let's take another example. So I'm just going to construct a random equation. So just construct on the right hand side 3 into 5 into 7, a number which is 3 into 5 into 7, or essentially 105. So it is a number of it is a number which is product of three distinct primes, and let's say on the left hand side you had x into x plus 1 into y, something like that, and we were asked that if this can be solved. So obviously from this equation it is pretty clear that x, x plus 1 and y in some order must be equal to the numbers 3, 5 and 7. So it might be very much clear that since x is if x is 3, then x plus 1 must be 4, but we cannot see any 4 here, right? So this is very much clear that this equation is not solvable. But how do we prove it? We cannot just write yeah, if it was more than a lot of distinct primes, we cannot just write that yeah, since x and x plus 1 both are not present on the right hand side, so that's not solvable. So that's not a good way to write it. So here you can always write that x into x plus 1 for any integer x is actually even, isn't it? So let's talk about positive integers first, and mostly you will be always be concerned with natural numbers. So let's restrict our solutions to natural numbers. So x into x plus 1 is even, and if it is even, then the LHS should be even. So we must have LHS as even, but we can clearly see that RHS is odd, and this is not possible, so there are no solutions. So this comes the contradiction. This comes as a contradiction. So here you see these are the basic techniques we can use. So let's talk about another problem. Let's talk about a problem which goes in this way: x minus y to the power 4 equals to 4. Now this is an actual problem that sometime came as a problem in some Olympiad. So I'm not gonna mention that, but let's just solve that as if it's a new problem, and let's just try to solve it. So x minus y to the power 4 equals to 4, and using the techniques we have discussed so far, we can solve this. To solve this, we need identity, a very famous identity indeed, which we call as the Sophie-Germain identity. So this is basically the Sophie-Germain identity, and many of you might have known this for long, and many of you might not, but it's okay because we are going to discuss it. So this is a very simple and basic algebraic identity. It says if you're given an expression of the form a to the power 4 plus 4 b to the power 4, and then this can actually be factorized into a product of two factors. So it's pretty easy. You just write a square whole square, and then you write 2b square whole square. Then you apply your formulas, which gives you a square plus 2b square whole squared minus 2ab whole square, because it comes as 2 into a square into 2b square, which is 4a square b square, which can be represented as 2ab whole squared. Now this gives you a square plus 2ab plus 2b square multiplied by a square minus 2ab plus 2b square. Now this is the entire thing here. So we can always factorize any expression of the form a to the power 4 plus 4b to the power 4. Now can we use this in our equation? Yes, indeed we can, because we can see, and yeah, I forgot to mention an extra factor, that x is a prime here. X is a prime. So using Sophie-Germain identity, we can write x equals to y to the power 4 plus 4. Now when x is equals to y to the power 4 plus 4, and we can always write this y to the power 4 as y to the power 4 plus 4 into 1 to the power 4, which exactly correlates with the Sophie-Germain identity. So it is clear that we can actually factorize the right hand side. So let's factorize the right hand side. So it was given as x equals to y to the power 4 plus 4 into 1 to the power 4. Now using the identity which we are going to see, just relate it, a squared, this a to the power 4, a is basically y here and b is basically 1 here, right? So a square plus 2ab plus b square, this thing will come as, since a is y, y square plus 2y, since b is 1 plus 2, into y square minus 2y plus 2. So let's write the answer: y square plus 2y plus 2, y square minus 2y plus 2. Okay. Now the thing is, since x is a prime, but we have expressed this as a product of two factors, but we aren't even sure that if it is actually equal to x or 1, right? So one more thing we can do here, we can just try to find the GCD. So in the beginning of the equation, we can do some routine checks that if x equals to 2, then obviously y to the power 4 equals to 2 has no solution. So x cannot be 2 and x is greater than 2, right? And if the GCD of the right hand side expressions is d, that is y square plus 2y plus 2 and y square minus 2y plus 2 has a greatest common divisor of d, and what this d might be. So let's see if we can find some conclusion. So d divides the difference of these two because it's the GCD, which gives you 4 into y. Now the fact is, since x is an odd prime, d can so since x is d also divides x, right? Since d divides the right hand side, d must divide the left hand side, so d must also divide x. So the thing is, there can be no integer d which divides x. So that's the first point, which gives us d is equals to 1. And even if we are tackling this equation, which we would get d divides 4y, so d must divide either 2 or d must divide either y, 2 square or y. So if d divides y, then obviously d must also again divide x. So this gives us a contradiction that d must be equals to 1 and then the numbers are co-prime. Now when the numbers are co-prime, then obviously they must be equal to x and 1 in some order. So the least of them, which is y square minus 2y plus 2, this is less than this because of the plus 2y and minus 2y factor. So we can easily write y square minus 2y plus 2 equals to 1, that is the lesser one, and y square plus 2y plus 2 equals to x. From this equation we can easily see that y equals to 1. So y equals to 1 was a double root of this equation of multiplicity, root of multiplicity 2, and putting in this equation we get x equals to 5, which is the only solution to our given equation. So x comma y equals to 5 comma 1 is the only solution to our given equation. So we use the Sophie-Germain identity, we use the concept of factorization to find out what the answer was, right? Okay, let's discuss a new technique, which is parametrization. Parametrization. So ignore the spelling, parametrization, and we're going to discuss it. So this is essentially means we need to introduce a new variable. So the key concept here is introduce a new variable and try to represent all of the existing variables in terms of this new variable so that you get a family of solutions somehow. So a good example of this is if you're given the well-known equation a square equals to b square equals to c square, which we also call as the Pythagoras theorem. So as we know that in integers this have a range of solutions which are infinite, right? So there are infinitely many solutions to this equation. So to understand how, we can always write the solutions ABC in a specific format, not necessarily including all the solutions, but we can write a set of solutions. So observe that if a is equals to m square minus n square for some integers m and n, which you can choose on your own, and if b is equals to 2mn, then c becomes equals to m square plus n square. So if a is equals to this, b is equal to this, and c is equal to this, then obviously we will have a set of solutions where you can put the values of m and n as much as you wish, right? So let's try m equals to 7 and n equals to 2. So this gives us the pair a, b, c equals to 49 minus 4, which gives you 45, 2, 4, 28, and then 49 plus 4, 53. So this again is a Pythagorean triplet where 45 square plus 28 square is equals to 53 square. So this essentially paves the way for a lot of calculation and a lot of answers. So obviously this is one way, but we are going to try and find how to do this. Okay, let's try an equation which came in previous RMO, that is Regional Mathematical Olympiad. So a problem of the kind x cubed plus y4 was equals to z to the power 31, where x, y, z were given as positive integers and you needed to find solutions and you needed to prove that the number of solutions of these equations are infinite. So whenever you get the hint that the number of solutions are infinite, you can always try and go ahead with parameterization. Now, in this kind of equations where the powers are very weird, I'm going to share to you a very well-known trick and a technique you can use almost anywhere to find infinite solutions. Is when you have two entries on the left hand side, choose a power of 2. And this power of 2, what you're going to choose, let this power of 2 be first a new variable u, and now the coefficient you are going to add on this, let this first calculate the LCM of the power. So if this power is p and if this power is q, where we have p equals to 3 and q equals to 4. So this power should be LCM of p and q divided by p, and the next power should be similarly divided by q. So this time it comes as 4, right? So x equals to 2 to the power 4u and y equals to similarly 2 to the power 3u. So this gives you the left hand side as 2 to the power 12u plus 2 to the power 12u equals to, and now choose z as any power of 2, like 2 to the power m, for example. So this gives you 2 to the power 31m. Since 2 to the power x plus 2 to the power x gives you 2 to the power x plus 1, because this is basically doubling the same number, and since the index is 2 itself, so this will give you 2 to the power 12u plus 1, which is equals to 2 to the power 31m. Now since you know 2 to the power x is a monotonic function, so its arguments must be equal if the values are equal. So we must have 31m minus 12u equals to 1 for integers m and u. And this is a linear Diophantine equation. So let me give you a bit of idea about this first. A linear Diophantine equation is an equation where ax plus by is equal to c, and this is solvable only and only if the GCD of a and b, which we call as d, divides c. So if c becomes 1, then ax plus by equals to 1 always has a solution, because any GCD d will always divide 1 whenever a and b are co-prime. So if a and b are co-prime like this, and then the x plus by equals to 1 has a solution, because 1 divides 1, right? So this is exactly the case of here, because you see 31 and minus 12, this is co-prime, and that should divide 1, which is on the right hand side. So this always has infinitely many solutions. Let those solutions be of the form m dot and n dot, like that. Let that be of this form. So in this way you can always find a set of solutions for this, and since this equation is infinite, there will be infinitely many values m prime and n prime which satisfy this equation, and putting that back you can always get the values of x and y which we derived, and similarly we can always answer that, right? So there will be infinitely many values of m and u which you can put to find a set of solutions. So that's a very neat trick for discussing parameterization problems. Now one last thing I would like to discuss in this class is the method of trying and using modular arithmetic in solving problems. So let's say you had something like x to the power 6 plus, let's say, 3x cube plus 1 equals to y to the power 4, and you had to solve it in positive integers x and y. So we where x and y are natural numbers. Now what to do with this equation? So there are a couple of key observations which we must know how to make when trying to solve any Diophantine equation, because this kind of questions will either come as a subjective if you are going for the ISI examination, or might even come as an objective, because this equation is very fit to come in an objective, because the number of solutions essentially is 0 for this one. So the question is, how do we know it? See, method number 1 is whenever you see even powers and a term corresponding to that, which really gives a hint for making it a perfect square, so just go ahead and make it a perfect square. So if the equation tells you to make it a perfect square, do it. So how do we make it a perfect square? We are not going to do this by writing 3x cube as 2x cube plus x cube. So remember, never split the terms. So try to make and try to utilize all of the terms. So just do it so that only the constant term becomes changed. So to do this, we multiply 4 on both sides, and by multiplying 4 we can get 4x to the power 6 plus 12x cube plus 4 equals to 4y to the power 4. Now write this as 2x cube whole squared. Write this as 2 into 2x cube, and we are left with 3. So we need a 3 square here. So let's make it a 3 square. And the right hand side comes as 4y to the power 4 plus 5. Because we added 5 more to make it a 3 square. And on the next step it should be 2x cube plus 3 whole squared, which means 4y to the power 4 plus 5 must also be a perfect square because the left hand side is. So essentially our problem is 4y to the power 4 plus 5 must be a perfect square, right? So there are essentially a lot of ways to treat this. So let's discuss the way which we should be familiar by now, that is factorization. So 4y to the power 4 plus 5 is equals to k square for some integer k, because we said it's a perfect square. It has to be, otherwise the equation has no solutions, because the LHS is a perfect square, right? Now if we take this to the right hand side, we get 5 equals to, and apply the formula, k plus 2y square into k minus 2y square. And as we can see that k5 is a prime, we can write 5 as 5 into 1 only. So the lesser of this, that is k minus 2y square, must be equals to 1. So k minus 2y square is 1, while k plus 2y square should be 5. Adding, we get k equals to 3. And using this value, we get y square equals to plus 1. And this gives you the value of y as plus minus 1. And the number of solutions which we got, by putting the value of y square as 1, we get y to the power 4 as 1. And obviously when you use this value, you get the answers x to the power 6 plus 3x cube equals to 0. And thus it gives you x cube into x cube plus 3 as 0. So the integer solution should be x equals to 0, right? If x is equals to 0, then only the LHS is 1. So the solutions are only 0, 1 and 0, minus 1. So whenever you have x and y as natural numbers, so this is violated, because x equals to 0 is necessary for this to have a solution, which we are not getting here. So x equals to 0 and y equals to 1, x equals to 0 and y equals to minus 1. So this 0 violates the condition of the natural numbers. That means it has no solutions in natural numbers. See how easily we can get this solution just by considering and completing into a square. So that's essentially the power of number theory and the power of Diophantine equations. Okay, so I guess I've discussed a lot in this video. So keep tuned for the next video, where we shall be discussing many more tricks and tips for Diophantine equations and other parts of mathematics which will be required for acing the examination. So thank you very much, and keep following Chinta. We'll meet very soon.